In the specialization Applied Nanophotonics, you will be researching photonics and then the interaction of light with the smallest particles on the nanometer scale.
The physical group studies flows across all scales, really from nanometers to multi-kilometer.
For the quantum specialization track, you will become the quantum specialist in these companies, which means you can learn about quantum field theory, perturbation theory, quantum optics, all the very specialized quantum topics.
Material science is the field where you grow, manipulate, characterize, measure materials, ranging from the quantum domain to the macroscopic domain, to learn from materials, but also to make them useful for society.
Quantum mechanics is booming business right now. It's all over the world. You see more and more companies popping up with quantum. But these businesses, they are growing fast, so we need more people to be educated in quantum. So you first have to do 2 mandatory courses. Everyone needs to do those, so quantum information and advanced quantum mechanics. And apart from that, you can choose to either specialize in quantum optics or you can specialize in quantum electronics. That's what I did during my PhD. For quantum electronics, you can think of topics like superconductivity, topological materials, Majorana fermions. All of these topics are addressed. You can do a more theoretical part within quantum electronics, so the computation, DFT calculations, using artificial intelligence within these calculations of the band structure of the materials. Or you can do a more experimental track and then you actually grow new materials, take a look at the materials, characterize the electronic properties. For quantum optics, there are a bit more mandatory courses. You, of course, have to do fundamentals of photonics. You also have to do the quantum optics and the integrated optics course. And after that, you can choose in which research group you will do your master assignment and where you will do your internship. But everything is focused on quantum optics. If you are interested in quantum mechanics, if you enjoyed these courses during your bachelor and would like to know more about it, would like to work in an upcoming business environment like quantum computing or quantum communication, then the quantum specialization track of applied physics is the track you should choose.
So light itself, already visible light, has a wavelength of about 500 nanometers. The interaction with particles is on even smaller scale. If you want to manipulate this, you have to have structures that are even smaller than this, so half the wavelength or quarters of the wavelength. And that means that you're looking to create structures and particles that are in the order of a few hundred nanometers. So one application that we're working on at the moment together with the Free University is looking at brain tissue from research into multiple sclerosis. We use a very special microscope, a microscope that can see contrast in particular molecules. So it's a chemically specific microscope which is sensitive to vibrations of molecules. Imagine that if a molecule consists of balls that are connected by springs, then they have a particular frequency at which they resonate. And that resonance you can lock into, and then you can create your contrast based on that, and you can see much more chemical information in the brain. The thing that I find fascinating is the interaction of light and matter. When light falls on something, what happens? Why does it happen? Why do these molecules and atoms get into an excited state? The fact that you can calculate the excited states so precisely. So for hydrogen, I think we're now up to 17 digits on the precision of the transitions. Why is this so precise? Why is it light that governs the structure of space? These are big questions. They don't normally come up too much in the general project. But even in all of these projects, there are interesting questions of what is happening with the light and the material. Why is it responding the way it is responding? Can we use this? Can we then make a little machine, a little thing that actually does something useful by having these elusive photons interact with whatever it is we're trying to measure?
So the group does a very large variety of flows, so really from the nanometer scale to the astrophysical scale, so solar systems, let's say. The nice thing about the group is that we do a combination of theoretical, experimental and numerical research, and these are generally also in close collaboration. So on the one hand, I perform most of the experiments with many of my colleagues, of course. But there's also a whole part of the group that does really numerical work on the computer. And then we often have the nice thing that we can then compare one-to-one really the experiments with computational models. And also sometimes we even are lucky that we can also do the theory, and then we can have let's say the trifecta. We can really do the three together and prove it from three different ways. And
So what kind of assignments should I think of?
Yeah, so there's really a large variety. So we've had people working on freezing. So how does freezing work on a small scale? We've looked people at wind farms, at droplet impacts, on printing, on biomedical flows, hardcore turbulence, turbulence with bubbles, particles or heat. It can be microfluidic scale, so really smaller than a millimeter, let's say, with particles inside or bubbles inside. It can really be a large variety. But to help the students, we have a page on our website with a whole list of possible topics to get a flavor of what we do. So I think a good example is, for example, in printing. In a normal inkjet printer, you have a little nozzle that creates the inkjet, right? This ink comes out and then deposits on the paper and evaporates, for example. So there's a whole complex process. So for example, this ejection mechanism we do in the lab. So we have nozzles from collaborators like Canon. We look at this ejection of these liquids, and these liquids are of course ink, so they have special properties that make it difficult. But then we can also use the properties of these fluids in computational models and compare them really one-to-one and explore things that are experimentally very hard, like measuring the flow inside a drop, which would be experimentally nearly impossible, but computationally very attractive to measure them.
As a student in the material track, you learn how you can manipulate materials, how you can characterize materials, but the most important thing you learn is what are the physics inside the material and what determines which physics I have. So for instance, it is determined by the structure of the material, the thermal properties of the material, and also, for instance, how a material behaves if I illuminate it with light. If I shine light on a material, why is it, for instance, conducting better? Or why would it change its shape? These are the kind of questions that you're trying to answer in the material track. If you make a material very small, although it is the same material as the bulk material, it behaves very different. So it means that confinement has a huge influence on how a material behaves. But you also learn on how can I measure these changes and how can I work with small signals? Because you can imagine that if you work with small materials, you also have small signals. A lot of things what we do is actually on a very small scale. So you need all kinds of special setups to actually investigate what you're doing. Because I can tell you that it is growing in a different structure, and then you say, oh, I believe you because you tell it's so nice, but you actually want to have evidence that this is happening. Yeah, so the machines that we use, it's a plethora of setups. So we use scanning probe microscopies, which means that we have small probes actually investigating the surface. So you have to think about scanning tunneling microscopy, of atomic force microscopy. But we also use a lot of X-ray diffraction, because with X-ray diffraction you can actually get out the crystal structure of the material. The thing that makes material science so exciting is that you work on the edge of what people know. So what we're doing actually is we're designing materials which are till this time not known, and to see if it exhibits very new physics. And the moment you see that materials behave differently than you expect, that gives you a really eureka feeling.